right? So let's discuss what happens if an object like this, okay, an object which can roll, is released on an inclined surface. Assume the angle of inclination is theta. First, let's assume the surface to be smooth. Okay. So some object which can roll is released on it. Assume it is released from rest. Let's say its mass is m, radius is r. Okay. One of you tell me what all forces act on this object.
The
What?
normal friction and its weight.
Smooth surface, why will friction act? Okay. Normal and weight. Fine. Weight mg acts this way. And normal force has to act at the point of contact perpendicular to the surface of contact. Therefore, normal force acts like this. Okay. You can resolve weight into components. Mg sine theta parallel to the incline and mg cos theta perpendicular to the incline. Okay. Now, in the absence of friction, these are the only forces acting. You can see their lines of action and all. You either consider mg as it is or you consider its components. Don't consider both because then you will be considering weight twice. We don't want to do that. So let's take the components only. Now tell me, what will happen to this object under the influence of these forces?
Sir, it will accelerate downward.
It will accelerate down the incline. Okay. Will it rotate?
Yes, sir.
No, because all forces have their lines of action passing through the center of mass of this object. So none of them can produce a torque. It cannot rotate. Fine. So it will simply slide down. If you mark a point here, point of contact, the same point of the object will always be in contact with the surface. So what you see is something like this. It simply slides down under the influence of mg sine theta and its acceleration will be g sine theta. Okay. What if it was a rough surface? Aishwarya, you try to tell me what would have happened had it been a rough surface.
Sir, it will rotate.
Okay. See, in the absence of friction, we have already visualized what happens. The point of contact skids down the incline. So to prevent that skidding or sliding, friction will have to act. Okay. The other forces will be acting as usual, the same manner. So mg cos theta, mg sin theta, normal force. Now, if it's a rough surface, friction will also act. And friction has to prevent sliding of the point of contact. Point of contact has a tendency to slide down the incline. Therefore, friction acts up the incline like this. And friction also has to act at the point of contact only. It can't act anywhere else. Okay. Aishwarya, you said it will rotate. Which force, which of these forces produces a torque and makes it rotate?
Sir, friction.
Friction is the only one which can produce a torque. Its line of action does not pass through the center. Good. Okay, so this object is going to roll down the incline. It translates as well as rotates. Now we'll make an assumption here. Assume friction is sufficient to prevent slipping. That means friction, what do you call? Friction enforces pure rolling. It makes pure rolling happen. So the point of contact does not slip. Okay. Angle of inclination is theta. right? Just write these equations and solve them first. Write F net equal to ma. Next, write tau net is equal to I alpha. And then friction is sufficient to prevent slipping means it will be under pure rolling. So A is equal to R alpha. Write these equations by using the forces that are shown in the diagram, and then solve the equations to calculate how much friction acts. Okay, try this. I'll give you all 3 minutes. Okay. Vanilla, tell me, how will you write the net force equation?
Sir, mg sin theta minus F equal to ma.
Okay. How will you write the net torque equation?
F into R equal to I alpha, sir.
Friction is the only force which produces a torque, and axis of rotation passes through the center of mass of this object. So perpendicular distance becomes its radius. So Fr equal to I alpha. We'll keep I as it is. We don't know what kind of object it is. We are deriving a general equation. And then A is equal to R alpha. If A is equal to R alpha, alpha can be written as A by R. So A by R. That means friction becomes IA by R square. Or you can write acceleration is equal to Fr square divided by I. This we'll substitute in the first equation because our aim is to derive the friction acting on it. Therefore, mg sin theta becomes equal to, send friction that side, F plus m into A. A is Fr square divided by I. So this becomes F into 1 plus mr square by I. Therefore, friction becomes mg sin theta divided by 1 plus mr square by I. Very useful equation. It can help you derive the amount of friction acting based on the type of object. If it's a disk, I is mr square by 2, ring, I is mr square, and so on. Okay. And once you know friction, see, acceleration is Fr square divided by I. You can derive acceleration also from this. You will get acceleration is equal to F is mg sin theta divided by all this into R square by I, because A was equal to Fr square by I. So send the I inside and R square to the denominator. You can cancel M. Effectively, you will end up getting g sin theta divided by 1 plus I by mr square. This is the acceleration with which the object rolls down, provided friction is sufficient to prevent slipping. Okay, so if it undergoes pure rolling, this much friction acts on it, and this is the acceleration with which the object rolls down. And you can see, greater the moment of inertia, okay, lesser will be this denominator. Okay, greater the moment of inertia, lesser the denominator. But if denominator is less, friction will be more. So greater the moment of inertia, greater the value of I, greater will be the amount of friction acting on it. And when it comes to acceleration, greater the moment of inertia, okay, greater will be the denominator, lesser will be the acceleration. Makes sense. If friction is more, obviously net acceleration will be less. Okay. Now you have some very common questions based on this. If a ring, cylinder, and a sphere of same mass and radius are released on an incline, which will roll down first? Okay. If it's a smooth incline, all of them will go down at the same time because they'll all go under the influence of mg sin theta, means they'll all have the same acceleration of g sin theta. Whereas if it's a rough incline and you are sure that they undergo pure rolling, then depending on moment of inertia, you can tell which will reach first. Now, whichever has more moment of inertia will have less acceleration, so it will go down slowly. Whichever has less moment of inertia will have more acceleration, provided the other terms are same. Mass and radius should be same. So suppose there is a ring solid cylinder. Okay, ring or hollow cylinder, their behavior will be the same. Disc or solid cylinder, their behavior will be the same. And then let's say there is a hollow sphere and a solid sphere, all having the same mass and radius. Then ring moment of inertia, you know, is mr square. Solid cylinder is like a disk mr square by 2. That is 0.5 mr square. Okay, first one is 1 mr square, next is 0.5. Hollow sphere moment of inertia is 2 by 3 mr square. 2 by 3 is 0.66. And solid sphere moment of inertia is 2 by 5 mr square, 0.4 mr square. So based on this, you can tell which will accelerate faster and all. Fine. Now, we assumed friction is sufficient to prevent slipping. So one of you tell me, friction should definitely act. Okay, otherwise it will skid. Friction will definitely act. And if it is preventing slipping, what kind of friction is this?
Static friction.
Static friction, correct. Fine. And then you can be asked questions like, they'll give you the length of this incline and ask you what is the speed with which it reaches the bottom of the incline, what is the omega with which it reaches the bottom of the incline, and such things. Once you find out acceleration, you can apply equations of kinematics to solve that. Okay. I mean, there are different ways to find out speed, final speed. Equations of kinematics is one method you can use. The other ways are work energy theorem and mechanical energy conservation also if conditions are satisfied. Now, if you want to apply work energy theorem or mechanical energy conservation, you should at least think of work done by all the forces. Okay. Now, you know what all forces act as this object rolls down the incline. Weight, normal force, and friction are the forces acting. Let us discuss how much work each one of them will do. Let's say this object is initially at the top of the incline. Top of the incline, it is released from rest. Okay. Length of the incline, let it be L. If length and angle are given, height is indirectly known. So H or L, any one of them will be given. Fine. Now the object rolls from that position to this position, bottom of the incline. And by the time it reaches the bottom of the incline, along the way, it experienced acceleration. It experienced net torque also. So angular acceleration also it would have experienced. Therefore, it would have gained some velocity and some angular velocity. Initially, it's at rest. It depends on the question actually. Initially, it need not be at rest also. It's not compulsory that it should be at rest. Okay. Now, equations of kinematics can help you find out that velocity because the incline was flat. Okay, so it always comes down with an acceleration of g sine theta by 1 plus I by mr square. Constant acceleration. You can apply equations of kinematics. But the problem arises when the surface is curved like this and an object is rolling down. Then acceleration will vary from point to point. Then you won't be able to apply equations of kinematics. In that case, if you want to find out final velocity or final angular velocity, the only two methods you will be left with are work energy theorem and mechanical energy conservation. So let's see. One of you tell me, what do you think will be the work done by normal force? Zero, negative, or positive? Exact magnitude we'll calculate later if necessary. Is work done by normal force as the object rolls down zero, negative, or positive?
Zero, sir.
Okay, we'll see. Aishwarya, what do you say? I just want the sign of work done by normal force. Okay, fine. Vanilla, why are you saying it is zero?
By any force is Fs cos theta.
Work
And
done by any
theta is
force is
90.
okay. So you are saying the angle between force and displacement is 90 degrees. That's why the work done is 0. Okay. The object is moving down the incline. So net displacement of the object is this way by an angle between normal force and displacement. Okay, we'll discuss that further. So you are saying it is 0. Next. Work done by gravity. Anyone? Is it positive, negative, or 0 as the object rolls down?
Positive, sir.
Positive. Okay. This is easy only. If an object descends, work done by gravity will be positive. If an object ascends, work done by gravity will be negative. So here work done by gravity is positive because it is descending. Next. What about work done by friction? Aishwarya, can you guess? No response. Okay, Vanilla, what do you say?
Negative, sir.
Work done by friction, negative. Okay. Why? Because force is up the incline and displacement is
Negative,
down the
sir.
incline. Okay. This is wrong. And the explanation that you gave for this is wrong. Okay, this is a very common mistake that students make. Work done by any force is integral F dot ds. F is the force whose work you want to calculate, and S is the displacement of the point of action of the force, not the entire object. The exact point on which the force is acting is what matters. Okay. Now, gravity is fine. Gravity does positive work only. Object as a whole is descending. That's fine. Now, normal force, if you see, normal force and friction, they both act exactly at the point of contact between the object and the inclined surface. Let's mark that point here, P. Now, this object is undergoing pure rolling. When object is undergoing pure rolling, the velocity of the point of contact with respect to the surface on which it is rolling is 0. If velocity of P is 0, that means ds by dt is 0. Okay, is my voice clear or is it breaking?
It's breaking.
Okay, just a moment. Right. So it was given to you that the object undergoes pure rolling, and when the object is in pure rolling, the point of contact will be at rest with respect to the surface on which it is sliding, on which it is rolling. So velocity of P is 0. If velocity is 0, that means ds by dt is 0, means ds is 0. Okay. So the exact point on which normal force is acting and also friction is acting is at rest. Therefore, whether you want to calculate work done by normal force or friction, in both those calculations, ds is 0, work done by both of them is 0. Friction does not do negative work as the object rolls down. Work done by normal force is 0 because ds is 0, not because force and displacement are perpendicular. Next, work done by friction is 0 for the same reason, because the displacement of the point of action of the force is 0. Okay. Now, gravity is the only force doing work, and gravity is a conservative force. Therefore, to find out final velocity or final angular velocity, you can apply mechanical energy conservation also. Okay. Potential energy lost is equal to kinetic energy gained. Fine. All this is true if friction is sufficient to prevent slipping. And if friction is sufficient to prevent slipping, as we have discussed, the kind of friction involved is static friction. Now, static friction has limits. we found that the friction required to act in this case, or friction that must act in this case, is this much. This is the amount of friction that should act. Now this should be less than or equal to mu s into normal force. Normal force here balances mg cos theta. By solving this equation, you can even tell minimum value of coefficient of friction. So a lot of questions can be asked based on this situation, and you can answer any of them. Fine, let's solve one problem based on this. So yeah, in questions, they won't give you all this anyway. Object is released on top of an incline. Assume angle 37 degrees for convenience. Let's say its mass is 2 kg. The radius is some 20 centimeters. Then m r square, r is 0.2, square is 0.04 into 2 is 0.08. So moment of inertia should be less than that. Let's say I is equal to mr square by 4. Okay. Some based on how it is made, how the object is made, or how the mass in the object is distributed, its moment of inertia is mr square by 4. Calculate all the values. Calculate how much friction needs to act on it. Assume pure rolling, okay? Assume pure rolling and initial velocity is 0. Calculate how much friction acts on it. Calculate how much acceleration it has. Calculate its velocity calculate the velocity with which it reaches the bottom of the incline also. Assume the height by which it descends is 10 meters. Okay, radius 20 centimeters we took. We are calling this as 10 meters. That is too much. Never mind. It is diagram and not to scale. Calculate these three values. Okay, if the object undergoes pure rolling, how much is the friction acting on it? How much is the acceleration with which it rolls? What is the final velocity with which it reaches the bottom of the incline? Okay, if you have not noted, you can note them down. The formulas for friction and acceleration, note down both of them. If friction is sufficient to prevent slipping, this is the amount of friction that acts. And in that case, this is the acceleration of the object. Okay. Use those formulas here and derive quickly. I'll give you all 3 minutes. You can directly apply the formulas. Friction is mg sine theta divided by 1 plus mr square by I. Okay. Now I is given mr square by 4. So mr square by I becomes 4. You don't actually have to substitute mass, radius and all. 1 plus 4 is 5. So mg sine theta divided by 5 is friction. How much is mg? 20. 20 sine 37 is 12. 12 divided by 5. That is friction. 2.4 newtons. Then acceleration. Acceleration, the formula is g sine theta divided by 1 plus I by mr square. Now I by mr square will be 1 by 4. Okay, 1 plus 1 by 4 is 5 by 4. So this effectively becomes 4g sine theta by 5. G is 10, 10 sine 37 is 6, 24 by 5, 4.8 meters per second square. And the speed with which it reaches the bottom of the incline, both of you gave answers as root 160 or 4 root 10. It's the same. But Pawan, you tell me, which method did you use?
Your v square minus u square equals to s.
Okay, equations of kinematics. Fine. So you'll have to find out this displacement first and then use v square minus u square is 2as. So v square minus u square is 0 anyway, is 2 into acceleration is 4.8. How much is the displacement? Slant length?
50 by
50 by
3.
3.
50 by 3. Okay. 2 into 4.8, 9.6. 9.6 into 100 is 960. Means 50 will be 480. Okay, we don't have to do that much. 480 by 3 is 160. Okay. Meter square per second square will be, then V becomes root 160, that is 4 root 10 meters per second. Okay. But one of you tell me, see, to use this approach, you will have to first derive acceleration. Sometimes you may not have that much time in the exam. Okay, or you may forget the formula. Like, see, it's just a question of I by mr square and mr square by I. That small confusion is enough to make you unsure of the acceleration. Okay, in your final exam, what's the guarantee that you'll remember this formula? So there's another way to find out the final velocity if you want, that is mechanical energy conservation. Let us try to do it that way. So we'll directly write potential energy lost is equal to kinetic energy gained. Potential energy loss is always mg into height descended by an object. Okay, by whatever height it is coming down, mg into that height is the potential energy it loses. If it rises up, it gains. Okay, so you can write potential energy lost is equal to kinetic energy gained. Usually we write ui plus ki is equal to uf plus kf. Now I'm taking a different approach. Okay, potential energy lost is mass into gravity into height descended is 10. Vanilla, you tell me, how should we write kinetic energy gained? Expression for kinetic energy gained.
Then half mv square plus half
Good.
I omega square.
You should write half mv square plus half I omega square also, because this object is rolling down the incline. It's not simply sliding. Okay. But there seem to be two unknowns here, v and omega. How to solve? Mass and moment of inertia are known, but v is unknown, omega is unknown. How to solve? You have to use the condition for pure rolling. V will be equal to r omega, means omega is v by r. So omega square becomes v square by r square. You can use that because it is v that you wanted to calculate. Convert omega to v terms. Now I is mr square by 4. So I by r square will be m by 4. So this whole thing, okay, keeping the half as it is, can be written as m by 4 v square. And then you solve it, you will get the same answer for speed. Okay, but the only thing you need to keep in mind is that you have to include kinetic energy in translation plus the kinetic energy of rotation. Okay, so that is how you solve when friction is sufficient to prevent slipping. Now in the same situation, assume object is released from rest, rough surface only. Let's say friction is not sufficient. In fact, you can find out also, as I said, you can find out how much coefficient of friction is needed. The required amount of friction, I'll do this quickly, is mg sine theta. Okay, you calculated it already, no? Friction was how much? 2.4 newtons. That is 12 by 5 newtons. This is the required friction to prevent slipping. The required amount of friction should be less than or equal to the maximum available friction. Maximum available friction is this much, mu into normal force. Normal force is mg cos theta. Cos 37, 4 by 5. So 5's cancel. 4 and 12, 3 times. So 3 by 20. So minimum coefficient of friction needed is 3 by 2 is 1.5 divided by 10 is 0.15. That much friction coefficient should definitely be there. If that much is not there, then friction is insufficient to prevent slipping. Okay, then the object won't undergo pure rolling. Now, if friction is insufficient to prevent slipping, first of all, one of you tell me, what kind of rolling does it do? Rolling with forward slip or rolling with backward slip? If friction is not sufficient.
With forward slipping.
Rolling with forward slipping, correct. Okay. You just imagine the situation in the absence of friction. In absence of friction, what would have happened? The point of contact would have skid down the incline. Skidding down means forward skidding. Okay. Now, friction is not sufficient to prevent slipping means it will skid forward only. So, translation will be more, but rotation will be less because friction is not sufficient. As a result, the point will skid forward. Okay. How much friction will act? If friction is not sufficient to prevent slipping, how much friction will act? Simple. If it's not sufficient to prevent slipping, the kind of friction acting will be kinetic friction, and kinetic friction has a direct formula, mu k into n. That's all. So mu mg cos theta, all available friction will be acting. So mg sin theta will be acting down the incline. Friction, all available friction, mu mg cos theta will be acting up the incline. Then you can find out acceleration and then solve the rest of the problem if you want. But in this case, if friction is not sufficient to prevent slipping, you can't apply mechanical energy conservation. Because if friction is not sufficient, kinetic friction will be acting. Kinetic friction will be doing negative work here. Okay? Because we know this is rolling with forward slipping. Rolling with forward slipping means the velocity of point of contact is in the forward direction. It's not at rest. Okay? So displacement of point of contact will be forward. Friction is acting up the incline, backward. So work done by friction will be negative. Some energy loss will happen. So if friction is insufficient to prevent slipping, you can't apply mechanical energy conservation. Keep that point in mind. Okay. Next. Just a moment. Assume a wheel is in pure rolling on a horizontal surface. So it's already rolling. Okay, omega is V by R. Such that the point of contact is not slipping. Now tell me, if this is a rough surface, does friction need to act? There are no extra forces. Weight and normal force are present. No extra forces. The object is already undergoing pure rolling. Does friction need to act? If yes, in which direction should it act? Think carefully. I'll give you all 2 minutes. V and R omega are equal. Surface is horizontal, rough. Should friction act or not? If yes, in which direction? Yes. What do you think? Should friction act or not?
So friction won't interact.
Okay. That is correct. There's no need for friction to act. See, friction comes into play when sliding has already started or if there is a tendency to slide. Now for this object, V is exactly equal to R omega. So it is translating and rotating in a balanced manner. And the forces acting on it are its weight and normal force, both of which pass through the center of gravity and both of which are vertical. So they won't produce horizontal acceleration, means acceleration is zero. and none of them can produce a torque, means alpha is also 0. That means A is equal to R alpha is also satisfied. Both sides are zeros. So it will continue pure rolling under the influence of these forces itself. Now, if it is anyway going to do pure rolling, what is the need for friction to act? It won't act. Okay. So here, even if it's a rough surface, the friction acting will be 0 because V is already equal to R omega. Had V not been equal to R omega, friction would have acted. Or had there been some other forces to disturb velocity, to produce acceleration, or to produce alpha in an imbalanced manner, then also friction would have acted. But here, nothing of that sort is present. So there's no need for friction to act. Okay. Now let's discuss that situation. Suppose there are two tracks like this. Up to certain distance, the tracks are horizontal. After that, they curve in the upward direction. One is a smooth track, smooth everywhere. The other is a rough track, rough everywhere. Now imagine this wheel is set into rolling motion on these tracks. On both tracks, it is initially in pure rolling. Okay, identical wheels. So for both of them, V is already equal to R omega. And the sense of rotation is also appropriate. They are both in pure rolling. Okay. Now, as long as they are on the horizontal part of the track, nothing will change. It will continue with the same velocity because there is no need for friction to act even if it is available. If it's not available, it will anyway not change. Situation will anyway not change. Okay. Once they enter the slope, okay, upward slope, think of what happens and try to answer which one will rise to a greater height. Okay. And it is given to you that the rough surface is sufficiently rough to prevent slipping. Okay. So on rough surface, you imagine there is no slipping. Means even when it is climbing up the slope, there is no slipping. Friction is sufficient to prevent slipping. Okay. So you just have to analyze and tell in which case the wheel will rise to a greater height.
రఫ్ సర్ఫేస్ లో చూసుకుంటే ఆ స్లోప్ ఎక్కేటప్పుడు అంటే హైట్ ఎక్కేటప్పటికి నార్మల్ కాంపోనెంట్స్ కూడా యాక్ట్ అవుతాయి కదా సార్.
Which components will act?
నార్మల్ కాంపోనెంట్స్
Normal force will act even on smooth surface. No? Okay. Aishwarya, what do you think? On which surface will the wheel rise higher?
Sir, on the rough surface.
Rough surface. Okay. Vanilla, what do you think?
Sir, I think it will be the same.
Same. Okay. So three different answers. Rishi, just take a wild guess. One wheel is rolling on smooth surface, one wheel is rolling on rough surface. In which case will it rise higher?
Rough one, sir.
Rough one. Let's see. See, even if you are given a rough surface in any problem, you will first have to visualize what happens on a smooth surface to understand how friction acts. Okay. So this object, since V is equal to R omega, it will continue pure rolling till it reaches the part where the incline is tilting upwards. Till then, V will not be disturbed. Omega also will not be disturbed because the only forces acting till then will be acting this way. Mg downwards, normal force upwards. Okay, so there's nothing to disturb V. There's no horizontal component. Okay, imagine it somewhere on this inclined part. Once it reaches this inclined part, the direction of normal force changes. mg continues to act vertically downward, let it be. But that also matters actually. mg acts vertically downward. Normal force acts perpendicular to the surface, means it acts like this. Okay. Now both of them still pass through the center. So none of them can produce a torque even now. So even when it is on the inclined surface, in the absence of friction, the net torque is 0. That means there's nothing to change omega. So omega continues to remain the same, even while it is ascending on the smooth surface. But see, while ascending on the smooth surface, the velocity will be in this direction. A velocity of any moving object has to be tangential to the path. So center of mass velocity will be in this direction. Now, if you see mg has a component opposite to that velocity. So that component of mg opposite to velocity, what it will do, it will slow down the system. Okay. F net is non-zero. And the net force is opposite to velocity here. I should not say net force is opposite to velocity. There will be some centripetal force also because it's following a curved path. Let it be. There is a force opposite to velocity. I'm not saying that is the net force, but there is a force opposite to velocity. Let me clarify this point also. Here, you can imagine a certain radius of curvature. Okay. Now, there's normal force and there's a component of mg like this. Let me call it mg cos theta. N minus mg cos theta should be providing the centripetal force. So N and mg cos theta are not balanced on a curved surface. On flat surface, they may be balanced, flat incline, but on curved incline, they are not balanced. Okay, anyway, put that aside. There is a force opposite to velocity, so its speed decreases. Okay, so as this object rises up on that inclined surface, the speed goes on decreasing. Omega does not change at all. So finally, when it reaches that maximum height, okay, where it cannot ascend any further, what happens on a smooth surface, in case of a smooth surface, is V becomes 0. It stops ascending, but the spinning will still be happening. Omega will still be there. And it will still be in the clockwise sense only. Why will it change the sense? It won't change the sense also. It will still be clockwise. And like that only, it will come down also because it's a smooth surface. Fine. So this is what happens if it's a smooth surface. And observe carefully, omega remains the same, means rotation remains the same, but V decreases. While it is ascending up, V decreases, means translation decreases. Less translation, more rotation means backward slipping. So as this object ascends, the point of contact slips backward. And if it slips backward, or if it has a tendency to slip backward, then in which direction should friction act? Forward, to prevent slipping. That is what makes this case interesting. So if it's a rough surface, no, friction actually acts up the incline. And if friction acts up the incline, it is actually helping the object move up. Okay, see, component of mg opposite to velocity is trying to slow it down, but friction is trying to speed it up. Why? Friction wants to establish pure rolling. Friction doesn't like slipping. Okay, so it wants to make the object undergo pure rolling. Now, due to mg's component, velocity has a tendency to decrease. Omega has no tendency to change. Okay, mg cannot change omega, but it is decreasing the speed. So what friction will do is, friction will increase the speed. But friction does something else also, side effect will be there. Friction creates an anti-clockwise torque now. Omega was clockwise, friction is creating an anti-clockwise torque. So it will decrease omega. It will increase V and it will decrease omega. It will try to keep them balanced. Fine. So friction acts up the incline. And as a result, what will happen? The object undergoes pure rolling and both v and omega will decrease slowly. Okay. Had only mg acted, v would have decreased much faster, but now friction is supporting v. So v won't decrease that fast. I mean, I'm not saying it won't decrease at all. V will decrease. The object will slow down, but it won't slow down as rapidly as in this case. Okay. So it will slow down. Omega will also decrease because friction is creating an anti-clockwise torque. So v decreases, omega decreases, and gradually they decrease, and both of them become zero at one point. But that point where both of them become zero will be higher in this case. Why will it be higher? Because friction helped it move forward. Okay. So in this case, on a rough surface, final v will be zero, final omega also will be zero. Pure rolling condition, v should be equal to r omega. So if v is zero, omega should be zero. Now, how do we say it goes higher? As I said, friction is helping it in climbing up. Okay. There's another way also to answer this. As the object rises up, be it a smooth surface or a rough surface, as the object rises up, it gains potential energy. Now, how high it goes depends on how much potential energy it can gain. Okay. Now, on a smooth surface, V is decreasing, but omega is not decreasing. So, on smooth surface, what is happening? The translational kinetic energy is getting converted to potential energy. Only translational kinetic energy is getting converted to potential energy. Rotational kinetic energy is still there in the object, even after reaching maximum height. But in case of rough surface, what is happening? Translational kinetic energy is decreasing, rotational kinetic energy is also decreasing, and mechanical energy is conserved here. Friction acting here is static friction, and it does not do any work. Okay, we had discussed this before. In pure rolling, static friction does not do work. So, translational kinetic energy is lost. Rotational kinetic energy is also lost. Both of them get converted to potential energy. That is why this height will be greater. The height attained in this case will be greater. Okay. So this is all slightly counterintuitive. On a rough surface, it goes higher than on a smooth surface. And then after reaching that maximum height, it will again come back rolling only if friction is sufficient. Okay. As it comes down, then friction will friction will continue acting like this. Omega. So mg component friction, they will give it velocity. Friction will give it omega. It will continue pure rolling down the incline also. Okay. Next. Suppose this is a rough surface. Wheel or disc or ball, anything you can consider. Let's say this object is initially at rest. Okay. Assume its mass is m, radius is r, moment of inertia is I. Moment of inertia about an axis passing through center of mass perpendicular to the plane of your screen. It's at rest. You strike the object. Okay, striking means giving it an impulse. Suppose you give it an impulse such that the line of action of the impulse exactly passes through the center of the object. Okay, means you have to apply a force for a short duration. You imagine hitting it with a hammer, okay, or something like that. Strike the object, give it an impulse. Giving impulse means what? Giving momentum. Okay, impulse is nothing but change in momentum. That is momentum after the impulse minus momentum before the impulse. Okay. Before the impulse, the object was at rest. Therefore, momentum after the impulse means mass into the velocity after giving the impulse will be equal to the impulse that you gave. So you know with what velocity it will start moving, j by m. So when you give it an impulse j, the object starts moving. Okay. Before impulse, its initial velocity was 0. Just after impulse, it will start moving with a speed j by m. Okay, let's call it u itself for now. Based on impulse, you can tell how much is the speed it gets. Okay. Now the forces acting, if you consider mg normal force, and impulse also would have been given by a force only. All three of them pass through the center, none of them produces a torque. So when you hit it in this way, what happens is the wheel suddenly starts translating forward without any rotation. So initial linear velocity will be non-zero, whereas initial angular velocity will be 0 after the impulse is given. Okay. So when the impulse is just given, the object is in pure translation, but it's on a rough surface. So you all think and tell me what will happen to this object. After the impulse is given, what will happen to this object?
So friction will act back.
Friction will act in the backward direction. Okay. As a result, what will happen to its speed? What will happen to its angular velocity? Till when does friction need to act? Comment on all those things.
So the object will start rotating.
Okay. See, we know that it skids in the forward direction. Therefore, friction should act backward. So after the impulse is given, it will gain some velocity, no angular velocity. So friction will act in the backward direction. Friction acts at the point of contact. So due to friction, it will start rotating. Okay. It will have an angular acceleration this way. But due to friction, it will have a linear acceleration in the opposite direction. So as a result, okay, someone else tell me, what will happen to its linear speed? Will it increase, decrease, or remain the same?
It will decrease.
It will decrease. What will happen to its angular velocity? Omega. Linear velocity will decrease. What will happen to its angular velocity? Right, increases. Friction produces torque. It will make the wheel rotate clockwise. So omega will increase. Initially, u is non-zero. Linear velocity is non-zero. Omega is 0. Means translation is more than rotation. Forward slipping. That's why friction is acting backward. But under the action of friction, what friction does is it decreases translation, increases rotation. So V will be decreasing, omega will be increasing, and that process will continue as long as friction acts. So friction continues to act, V continues to increase, V continues to decrease, omega continues to increase. Then at one instant, okay, at some instant, definitely V will become equal to R omega because V is going on decreasing, omega is going on increasing. Then at some instant, V should definitely become equal to R omega. Pure rolling will be established. And once pure rolling is established on a horizontal surface, friction does not need to act. That's all. So till pure rolling is established, friction will act. After that, friction doesn't need to act. It's a horizontal surface, no? Once V becomes equal to R omega, friction, it means friction has prevented slipping. Okay. And after that, there's no force to increase V or decrease V, increase omega or decrease omega. The system will automatically not be disturbed after that. So system will continue pure rolling after that. Then there's no need for friction to act. So once V becomes equal to R omega, friction stops acting. Is this clear to all of you? Are you all able to imagine what exactly will happen? Any doubts? Okay. So let's solve a problem based on all this. Impulse and all, it's okay. They can give the question in terms of impulse, but using impulse, you have to find out initial velocity and initial angular velocity. Okay. Let's say that part is done. So the object is placed on a rough surface and it is kicked in the forward direction. So it got that velocity, but it didn't get any omega. Mass is m, radius is r, initial speed is u. Okay. Friction coefficient, you can take it as mu. Why do we care about friction coefficient? Because the kind of friction acting here is kinetic friction. Because till pure rolling is established, the point of contact will be skidding forward. And if it is skidding, kinetic friction will be acting. You know how to write the formula for kinetic friction also. Okay, let me give you values. Initial velocity, let's take 10 meters per second. Mass 2 kg. Radius, okay, for convenience, let it be 1 meter. Moment of inertia depends on the system actually, but it cannot be more than mr square. So cannot be more than 2. Let's say it is 1 kg meter square. This also for convenience, I'm giving you an easy value. Coefficient of kinetic and static friction, take it as 0.5. Okay. I want you to find out what is the final speed it attains once pure rolling is established. Okay. And you should also find out how much distance it travels, how much distance the center travels before attaining pure rolling, and how much time it takes also, all these things. Distance, time before it attains pure rolling, and what is the speed when it just attains pure rolling. Think carefully and solve. I'll give you all 3 minutes. You know all this is happening due to friction. Friction itself produces acceleration. There's no other force to produce acceleration. And friction itself produces torque. Okay. Keep these points in mind and solve. So let's first visualize the forces acting on it. One is its weight, which is 20 newtons. Normal force will be balancing its weight. So normal force is also 20 newtons. And because it is skidding in the forward direction, kinetic friction acts backward. Formula for kinetic friction, mu k into n. Mu is 0.5, normal force is 20. So friction acting is 10 Newton. Till it attains pure rolling, the same 10 Newton friction will act. Means constant force, which results in constant acceleration, which means you can apply equations of kinematics. Okay. Force is 10 Newton. That itself is the net force. Normal and weight are balanced. Therefore, net force 10 is equal to mass into acceleration, means acceleration is 5 meters per second square. You are supposed to take it with a minus sign because it is opposite to initial velocity. Only then you can properly apply equations of kinematics. Okay. First, if you want to find out the distance traveled before it stops, you know initial velocity, you know final velocity also, 0. Okay, wait. This is not stopping. This is attaining pure rolling. We don't know final velocity. Let the final velocity be V. Okay. And let final angular velocity be omega. We know the relation between them. We know the relation between V and omega because it attains pure rolling ultimately. So V is equal to R omega. If one is calculated, the other is indirectly calculated. Okay. Right. Now the time in which velocity changes from 10 meters per second to V, in the same time, omega will change from 0 to omega. Okay, angular velocity will change from 0 to omega. So we can write one equation for linear velocity in terms of time. We can write one equation for angular velocity in terms of time. And we know the relation between linear and angular velocities. From there, we can calculate time. Okay, let's see how all this can be done. Acceleration is 5 meters per second square. Put that aside. The only force producing torque is also friction only. Friction. Because weight and normal act through the center. They can't produce torque. How much torque will friction produce? Friction multiplied with the radius 1 meter. So net torque is 10 is equal to I alpha. How much is I of this object given to you? 1 meter per second square, 1 kg meter square. Therefore, alpha is 10 radians per second square. Okay. This you can take positive because initially omega was 0. So if you consider alpha positive, then omega also will come out positive. That's fine. We know A, we know alpha. Both are constants. So we can apply equations of kinematics. Till it attains pure rolling, they are constant. So first, V is equal to U plus AT. U is 10 plus acceleration is minus 5 into t. V is unknown, t is unknown. So we can't solve this equation yet. Next, omega is omega naught plus alpha into t. This is another equation. And then we know V is equal to r omega. Now how much is the radius of this object? Radius is given 1 meter. So it's like V is equal to omega because r is 1. Now you just equate these two. 10 minus 5t is equal to 10t. Means 10 is equal to 15t, t is equal to 10 by 15. 2 by 3 seconds is the time in which it attains pure rolling. Vanilla, what mistake did you make? How did you get root 38?
Sir, I wrote the equations wrong.
Okay. So you get the time this way. Then substitute this time in any one of these equations. You can get V, you can get omega. Once you get V, okay, by using this equation, you can use V square minus U square is 2as and get the distance traveled also before it attains pure rolling. So is it done? Distance, time, final speed. Okay, you can find out everything this way. There is another approach also you can take to solve problems like this. I'll just give you the idea, or okay, we can apply it also. It won't take long, just 5 more minutes. We want to find out the final angular velocity and final speed, no? I'll tell you what can be done. Omega naught is 0. You see the forces acting, weight, normal force and friction. Weight and normal force are balanced. Means they can't produce net force, they can't produce net torque also, and they can't produce net torque about any axis, not just the center. Because they are balanced forces. Okay. Friction is the only force which may produce torque about some axis. Now, why am I talking about torques and axis? That should have given you an idea. Actually, we are trying to identify an axis about which net torque is 0. You can consider an axis lying on the ground. Perpendicular to your screen lying on the ground. If you consider an axis like that, the net torque about this axis becomes 0. Mg and normal, Mg produces maybe anti-clockwise torque, normal produces a clockwise torque, but they'll balance. So net torque due to them is 0. Friction's line of action passes through that axis. So friction cannot produce a torque about that axis. So net torque is 0. Okay. Now what is happening to this object? Speed is decreasing. Omega is increasing. So finally, it will have some speed and some omega value once it attains pure rolling. The question was to find out those values. Let's say the speed is v. Let's say angular velocity is omega. We know omega is equal to v by r. Radius in this problem is 1 meter. So omega is also equal to v only. Okay. Numerically, it is equal to v. Now, if net torque is 0, which principle of physics can be applied? Or which fundamental law can be applied?
The conservation of angular momentum.
Conservation of angular momentum. And about whichever torque, whichever axis net torque is 0, about the same axis you are supposed to apply conservation of angular momentum. So we are now going to write initial angular momentum about this axis is equal to final angular momentum about this axis. Let's see if we get the same answer or not. Initially, when the impulse was just given, this object was in pure translation. In pure translation, how do you write angular momentum? M RCM cross VCM. This is the line of action of velocity. Perpendicular distance is the radius. So initial angular momentum is mass of the object, perpendicular distance, initial velocity. Initial velocity is 10. So M R perpendicular into V. There is no initial rotation. So I omega naught, this part is 0. So this is the total initial angular momentum. Should be equal to final angular momentum. Finally, the wheel has a speed V. So its angular momentum due to translation will be M R perpendicular into V. Next, finally, the wheel is rotating also. So I omega also will be there. I is given as 1 in this problem and omega is equal to V because the radius is also 1. That's all. So 20 is equal to 3V. So we are getting V as 20 by 3 meters per second. Let's see if we got the same velocity earlier also. We got time as 2 by 3. If you put time 2 by 3 here, 10 minus 10 by 3. 10 minus 10 by 3 is 20 by 3 only. Okay. So this is another way to solve such problems. But this way, this approach can't give you all the answers. It can't tell you how much distance it traveled because angular momentum conservation does not involve this distance. It can't tell you how much time elapsed also. Okay, so those things cannot be found using this approach. But if you just want to find out final velocity, final angular velocity, you can do it. Okay, take any good book for JEE preparation. You will have questions based on this. In HC Verma also you may find. Otherwise, okay, I'll send you some problems you can solve. So we discussed rolling on an incline, curved incline. Then this case where it attains pure rolling after some time. Fine. Next class we'll discuss shift in normal force and toppling of an object. With that, the chapter will be complete.